Hi, welcome to part 2 of a video series I'm calling Thinking While Using the Graphing Calculator. Excuse me. In part 1 of this video lesson, we figured out what we need to do to be able to see a reasonable graph of a surface area function for this imaginary box that's being built. In the process, we were able to define the independent-dependent variables, figure out what a reasonable domain was, and using context clues and our common sense, we were able to program the calculator to tell us what kind of y values to expect, hence the range. Using all that, we set up an appropriate viewing window so that we will see the parts of the x-axis and y-axis that will reveal the solutions we're interested in. And finally, we studied a little bit more about the graph using the value key. Now, this part right here we didn't talk about in class, but once the graph is visible, you should describe to yourself, in terms of thinking, what does it actually say about the function? So if I looked over here and just looked at what I see, I would see that as I increase the size of the base of the box, it enables the surface area to cover that box to get less and less and less. So in other words, I'm becoming more efficient because I'm using less surface area to hold the same amount of volume. However, somewhere here around 5 or 6 centimeters, it suddenly starts to, the surface area suddenly starts to increase. So if I make the bottom of the box too big, then I'll start needing more paper to make the bottom and the top of the box, and that increases the overall total surface area. So this graph suggests that there's a perfect place to build the box, that is to say a perfect dimension to build the box, so that it will always have a 200 cubic centimeters but require the least amount of paper possible. This is how manufacturers are able to develop the most efficient shipping size boxes by using the least amount of materials to hold the most amount of stuff. Anyway, all of this is, again, just the stuff that I think about before I actually get to answering any sort of question. So the question at hand is, well, it says determine an appropriate viewing window that will show the features of the graph, construct an accurate detailed graph that reflects what you saw on your calculator. So I can't see your calculator, so I'm going to need to see what you saw. Now, if you recall, on the previous video, I found specific values for when x equals 2, when x equals 6, and when x equals 12. I think it was 10 in the video, but whatever. I use those points from the calculator to put 3 points on my graph. Now, I want you to notice, when I made the graph, I used the ruler to set my scale, and that scale reflects exactly what I saw in the graphing calculator. I also used a ruler to set this scale here. Then, when I plot the point to 400, or whatever that point is, I use my ruler, and I actually follow the ruler up to put my point there, so that I'm using the scale on the ruler, which exactly reflects the same scale that I used to create this y-axis. So in other words, plot these points as accurately as you can so you can use the graph in later reference. Then, the rest of the points don't have to be plotted, they should just naturally follow the shape of the curve. So, this is what I would write down for part A. Everything that you see here, I've got details, I've got labeled x and y axis, I used this ruler to scale off my x and y axis, and I carefully plotted and tried to reflect the graph as closely as I could. Well, that was sudden. So, another thing that I'm going to write down, if this was a test, for example, is I'm going to jot down a couple of the mental notes. I can't write down everything that I was thinking during the thinking and planning stages, or thinking and praying stages, but what I can do is at least jot down a couple little notes to myself and to the reader, just to make sure it's clear that I'm thinking about what I'm supposed to be doing. So here's some ideas. Identify the dependent variable and the label or units that it's measured in, and understand what it's for. Identify the independent variable and how it's measured in centimeters, what it represents. And then I also take a little note about the fact that what is this volume supposed to be here? The volume is fixed, but according to my equation, the area changes as the dimensions of the box change. So these are just little notes to myself to prove that I understand what I'm talking about. Part B asks me to find A of 5 and to talk about what it actually means. The first part, I do A of 5. Notice I did this work without a calculator. I know the calculator is available and we're trying to learn how to use the calculator, but it's a worthwhile exercise to test your number skills. We can always back it up with the calculator if we want. Anyway, I have to interpret the meaning of this, and so I use conversational language. If the base of the box was a 5 by 5 centimeter square, then it would take 200 square centimeters of paper to make that box. I indicate where on the graph that exists. So if I want to make this in a better answer, I could say making a slightly larger box would result in a smaller surface area. So if I was interested in reducing the surface area required, I would make the base of the box slightly bigger, and I could find that point if I wanted to. The other thing that can be done to improve this is to actually show the geometric shape that is optimal here. That is to say, what is being described by this fancy function equation. So the work that I'm doing down here indicates that I know I'm dealing with a 5 by 5 box, and I need to find the height. I found the height by using my understanding of volume. It's base length times width times height. We know the length and the width, and so we just divide to find the value of h at 8 centimeters. So the box that I'm building is not only going to have a surface area of 210 square centimeters, a volume of 200 square centimeters, which, by the way, 5 times 5 times 8 is 200, but I could also now look at all the panels. There are 4 panels that are 5 by 8. Boom, 4 5 by 8 panels. There's a top panel and a bottom panel that are 5 by 5, so I got 2 of those. And I add it all up and I get 210 square centimeters, completely consistent with what my function said. So now I'm proving that I understand the geometry that underlies all of this graphical analysis. This stuff at the bottom is not necessary to get an A on a test. I'm just demonstrating how we can go a step further if we ever had the time. This stuff in purple down here is only stuff you do if you're absolutely finished with the test, and rather than hand it in, you want to spend some time embellishing. So that's what that's about. I guess that's all I have to say today. Oh yeah, there is one last thing. The homework that we need to do for the next lesson is right here. This is, I can't remember what page it's on in your packet, but it's the next section that we're on. And in each case, all I need you to do is just state the independent, dependent variables, and then make a graph. Using the appropriate viewing window, make a graph that correctly resembles each function here. Use context clues just like I did. Use common sense and understanding of the nature of the problem like I did. Make a viewing window and then put the graph on paper. So tomorrow what I'd like to see is 4 graphs. 1 graph for this function, 1 graph for the function in number 2, then here's number 3 on the same page, I believe, and number 4. So I want to see a graph for each of these functions. Those graphs should be generated from the graphing calculator. The rest of the questions we're going to handle later, but before we answer any of these questions, we should actually be making the graphs and learning how to use the calculator. So, hope that makes sense. If you have any questions, let me know. Have a great day.